So now that we've talked a little bit about the atmosphere, we've got just a general knowledge of what weather is. We're going to begin to work on what we would call different variables in the atmosphere, things that change with time. One of those will be temperature, another pressure. And why do things change with time? Well, what gives the atmosphere the ability to change those things? And it's the sun. The sun provides the energy for our atmosphere. So without the sun, pretty much I wouldn't have to worry about weather. But we wouldn't have a life here either without it, so that would be a problem. So let's take a look at the sun a little bit here. We got to understand a little bit about how energy flows into the earth and out from the earth. So we're going to talk about electromagnetic radiation. You deal with it every day, believe it or not. You use microwaves to heat your food sometimes, or maybe you can see each other. That's visible light. Maybe you turn on a headlight in your car. Again, that is a light. That's an electromagnetic radiation. So these are waves of energy that flow through the atmosphere. They can be all kinds of different sizes. If you run a radio station, you have one. Your radio station's on a certain wavelength. If you look at the sun, that's outputting light at a different wavelength. So we're going to talk a little bit about, we got to have a little fundamental understanding of these waves in order to understand how they transport energy in and out of the atmosphere. So what is a wavelength? Well, I like to look at the ocean, and I go out in it as much as I can when it's warmer. I don't go out in it today when it's cold. But there are waves out there all the time, and they kind of hit you one after the other. Well, you think about it, that wave hitting me is a peak. It goes down the water, and then the next one hits. The length between those two, times it clobbers me sometimes, is a wavelength. The closer they are together, the shorter the wavelength. More of them that'll pass at one point. Now, electromagnetic radiation always moves at the speed of light, which happens to be 186,000 miles per second. So, the more of them that are grouped together, the higher the energy is. The shorter that wavelength. The longer the wavelength, the less the energy. We all absorb radiation, and then we transmit it out. And most of us, believe it or not, are what you would call a black body, which means if you look at an object, it takes all that energy it received from the electromagnetic radiation and radiates it right back out. So we approximate most things as black bodies. And with that, we can do a little bit. A black body is inversely proportional to its absolute temperature. So, if the temperature is really, really hot, say the sun, then we're going to have very, very short wavelengths. However, say it is extremely cold, we will have less wavelengths. We further apart. But it'll still be transmitting energy. And here you can see how the sun's radiation, the visible light that we typically see, is pretty close to the sun's radiation. Another interesting thing is that energy is equal to the fourth power of the temperature of that object. So if you have a very, very hot object like the sun, even compared to the earth, which is a lot colder, 4 times that temperature is multiplied each other of the sun. So it gets really, really a big number. Whereas the earth, much lower, it's not nearly as big a number. So another interesting thing is the further from the sun we are, the less we get the radiation from the sun. So by, say, tripling the distance from the sun, we would have 1/9 the amount of radiation you would get typical from the sun. So if our radius from the sun was 3 times more than what is the Earth's, we would have 1/9 the amount of solar radiation. If that radius was less, we'd have more. Here's where it gets a little bit more complicated. You ever notice your shadows? Think about it. When you're outside, you have a shadow. In the wintertime, that shadow is actually longer than it is during the summertime. And if it's noon, it's going to be a little shorter than if it is later in the day. Why is that? Well, the sun is actually hitting you at an angle. It's not directly overhead. Now, if you went to the equator or down in the tropics, the sun would be directly overhead. So yes, at noon, you might not have hardly any shadow at all, if any. But up here at noon, in our latitudes where we live, we have a shadow because the sun is coming in from an angle. If you did it with a flashlight, you would notice that the area of the sun's energy, the flashlight's energy, is pretty intense if it's pointed directly down. But when it's pointed at an angle, it's going over a much larger area. Same amount of energy coming out, but it's covering a bigger area. Same thing happens to the sun. So, if you're at further and further north or south, away from the direct sunshine at the equator, the sun's energy, while it is the same, is covering a larger and larger area. So that if you pick a given point in that area, you're not getting as much energy as you are if you were at the equator at one individual point. That's why we have an uneven distribution of solar radiation around the Earth. One of the reasons. We also have the little problem that the Earth is tilted. I know we don't like to make anything simple here. But by the Earth being tilted, it means that as it is rotating around the sun, it keeps changing how it's oriented towards the sun. In the summertime, the northern hemisphere is tilted toward the sun. In the wintertime, the northern hemisphere is tilted away from the sun. So, guess what? As of now, that sun is coming back north because we're heading back towards summer. I have a friend lives in Burlington, Vermont. Loves winter, hates summer. Always. Every time it would hit June 21st, when the sun was beginning to move back south, he would let me know winter was coming. Because at that moment in time, the sun was beginning to move away from the northern hemisphere. I could argue the same thing. On December 21st, that sun had begun to come back towards the northern hemisphere. And here you can actually see that in a demonstration. Here is our winter time, our tilt. The tilt never changed. It's just the way it rotated around the sun so that it winds up June 21st. So all this solar radiation comes into the Earth's atmosphere. What happens to it? Well, some of it gets scattered, some of it gets reflected, some of it gets absorbed, but all of it, 100%, has to be accounted for somehow. What do you mean by scattering? Well, if you ever look at a bright cloud up in the sky, the sun hits that cloud and it scatters it all over the place, the rays from the sun. So part of them come to Earth, part of them go up. The daytime sky is blue because of scattering of that radiation. There's reflection, which is called albedo. You ever walk outside after you had a very fresh snowpack, and yet it's a very bright, sunshiny day? Well, you probably have to wear sunglasses because of that. That sunshine is bouncing off of that snow because snow has a very high albedo. So it's just reflecting all that radiation back that hit from the sun. That's why it's staying so cold. Absorption is different processes can absorb energy. The Earth's surface, the atmosphere itself, depending on what type of gases are in the atmosphere, absorb it. That's how we start beginning to talk about the greenhouse effect. And if you look at solar radiation, and its curve here, you can see further north, we get less. And you can see where it's over a snowpack, like this satellite picture shows here, coming down in the mountains of West Virginia or right along Lake Erie here, we'll have much less, and it'll be colder because of that. And here you can see the planetary budget. 30% of the radiation coming towards Earth is reflected by the Earth's atmosphere. Another 23% is absorbed by the atmosphere itself, and then 47% of the rest of it, or the majority of the total, is absorbed by the Earth's surface, heating the ground. So the Earth's surface is also the main source of heat for the atmosphere. It begins to warm the temperatures at the ground first. So one of the interesting things is we need a greenhouse effect. Our Earth would be a lot colder without the greenhouse effect. So, however, we want to keep it balanced. We want to, a certain amount of temperature is good. A little too warm is not so good. A little too cold is not so good. So, over the years, greenhouse gases impact our Earth. Greenhouse gases are transparent to visible radiation coming from the sun. So in other words, a greenhouse gas will let the sun's radiation in, reaching the Earth's surface. Now, remember, the Earth is a black body. It radiates back out, but remember, it's a whole lot colder than the sun, so it radiates out a different wavelength. That wavelength, however, is absorbable by these greenhouse gases. So they absorb that radiation, and they send some of it back into space, some of it comes back to Earth. So that is why we stay warmer. We have at least some of that radiation coming back to heat us up and keep us a little warmer. The principal greenhouse gas is water vapor. That is the main one. Second is carbon dioxide, then ozone and methane. So let's think about why we would call water vapor the principal greenhouse gas. If you live in a very humid climate, you have a lot of moisture in the air. But what happens at night? Well, at night, the Earth is emitting a lot of infrared radiation, whereas during the day, the sun's radiation is strong. So at night, that infrared radiation in a very humid atmosphere is getting absorbed by that water vapor. That water vapor then radiates some of that infrared radiation back to Earth and heats it up. So at night, the temperature doesn't fall very fast in a very humid atmosphere. Now, so let's take a look at a desert. A desert, on the other hand, has no moisture, very little anyways. At night, it gets cold really, really, really fast. And it gets quite cold. Why is that? Because there's no moisture there. So that greenhouse gas is not there and impacting it. They have been studying greenhouse gases for a while now. And you can see the steady curve upwards of carbon dioxide here at Mauna Loa. Oh yeah, during the summertime, of course, photosynthesis occurs in the northern hemisphere. More of it. That actually drops the amount of CO2. However, in the wintertime, CO2 is going to go back up. All right, so I wanted to show you this on terms of satellite. And I wanted to just show you here is actually night and day. You can actually see it moving along here. So notice it's still dark a lot longer up here. If you went to latitude, went on a longitude, would go like this. So you would think, oh, everywhere is changing. No, it stays dark a lot longer in the north in the wintertime and a lot shorter time in the south, down towards the equator. So you can actually see the sun moving across the earth as it's doing this, and just what we were talking about. Now, if I wanted to look at all kind of radiation coming back out from the earth, I could do that. This is just a GOES satellite channel. We're looking at all different wavelengths here. So, for example, 0.47 microns or 0.64 microns, they're visible. 0.68 and more vegetation. We look maybe at cirrus clouds at 1.3. There are, all told, 16 different channels we're looking at, all with different characteristics, all looking at different aspects of our atmosphere and how radiation is transmitted. So, hope you got a little bit out of this. I know it can be a little complex. Please don't hesitate to ask if you have any questions.